Hello mathematicians, today we're going to be looking at vertex form of a quadratic. So we remember that quadratics are expressions that have a squared term in them for our variable, and that's not the same as having 2 to the power of x, for instance. It's not the same as an exponential function where we have the variable is in the exponent or the power. Here the base is our variable, but then we're raising it to the power of 2. And we might have other terms in that. In general, we've seen f of x equals ax squared plus bx plus c would be our standard form. Okay. And we've also seen the factored form where, depending on where our graph crosses the x and y axis, specifically the x-axis is going to help us. We can link that with what the factors are here. The vertex form is going to tell us, as you might imagine from the name, more information about the vertex, where we can see right away from the equation what that vertex is going to be. So let's get started. First of all, with a notice and wonder for our warm-up. Take a moment to look at these two sets of equations and type, what do you notice and what do you wonder? Some possible observations you might have made or things you might have noticed. Each set has 3 equations. Set 1 has 3 equations. Set 2 also has 3 equations. You might have noticed that each equation has the output in function notation on the left side of the equal sign and an expression on the right side. So remember that this f of x means function notation where f of x means that x is the input and f of x would be the output. Okay, so they're in function notation, all of these equations. And also we have expressions in standard form and factored form and one other form. So these top 2 are standard form. Factored form, we have the different factors. So for instance, we can see that 5 minus x times x minus 1, if we were to multiply that out, we would actually get the same thing, the negative x squared plus 6x plus 5. So these ones are actually equivalent. Same thing here, if we were to multiply our factored form, which has the factor x times the factor x plus 4, if we were to multiply those, we would get x squared plus 4x. So we know that the top 2 equations in each set are equivalent. Things we might wonder about. Why are the equations in this set grouped together? So what's going on that's special with set 1? Why are those together? And how about set 2? Why are those ones together? Another thing you might wonder is, in each set, is the expression in the last equation written in a particular form? What is it called? Well, spoiler alert, it's going to be called vertex form, which you've seen because we have the learning targets on the last slide. In each set, is the expression in the last equation equivalent to the other 2? And that is going to be the question that guides our work on the next problem. So our first activity after the warm-up, we have 2 sets of equations, the same ones that you saw earlier. In each set, the expressions that define the output are equivalent. They are the same. So we have an example here that shows us the expression that defines h. So here we have h of x is written in vertex form. So we don't yet know exactly what the rules are for vertex form, but this is something that's written in vertex form. We can show it's equivalent to our expression defining f up here, so we can show that it's an equivalent function by expanding the expression. So the x squared, the x plus 2 squared minus 4. X plus 2 squared. Careful that we don't just try and have just x squared and 2 squared. That's not correct. We need to make sure something squared means multiplying that by itself. So x plus 2 times x plus 2. One way we can do that is with our rectangle here. We have x plus 2, x plus 2. X times x will be x squared. 2 times x is 2x. X times 2 is 2x, and 2 times 2 is 4. So that gives us x squared plus 2x plus 2x plus 4. And then we still have this subtracting 4 happening at the end. When we combine like terms, the 2x plus 2x makes 4x, and the 4 minus 4 would be 0. So that means that x plus 2, that expression squared minus 4, is equal to x squared plus 4x. So it's equivalent. What we're going to do now is show that the expressions defining r and p are equivalent. So r is this one, and p is this one. And we're going to show that by taking r, just like we did up here for h. We're going to take r, and then we're going to see what happens when we expand it. So we have -1 times, let's do r, x plus 3 times x plus 3. X times x is x squared. X times 3 is 3x. 3 times x is 3x. And 3 times 3 is 9. So we have x minus 3 squared can be replaced with x squared plus 3x plus 3x plus 9. And then let's be careful not to forget the plus 4 that's going on over here. So we expanded, or we multiplied the x minus 3, that quantity squared, but then we also have to add the plus 4. So let's see what happens now. If we distribute this -1, we have -x squared minus 3x minus 3x minus 9 plus 4. And that came from distributing the -1 to each of the other terms being added together within these parentheses. When we simplify that, that's going to be just like before where we combined like terms, so -x squared, okay, and minus 3x, we get minus 6x, minus 9 plus 4, we get minus 5. Notice that that is exactly the same as what we have here for p of x. So here we have the graph of h, and we have the graph of r. And we're going to answer now, why do you think the expressions such as those defining h and r are said to be written in vertex form? You may notice that if we look for the vertex for each of these graphs, for the graph of h, in factored form we recognize that the intercepts for the x-axis are at x and are at 0 and -4. For the vertex, though, we would go and find the coordinates of this point that's at the center of our quadratic. It's on the axis of symmetry, or the part that would cut the parabola in half. And we have -2, comma, -4. And here we have, going to the right, 3, so 3, comma, and then up 4. So how do we see the -2, -4 vertex of h relating to the equation h of x equals x plus 2 squared minus 4. All right, so now we're going to take a look and explore what happens if we are adjusting in these same ways, adjusting the equations, but not just in standard or factored form, seeing what happens if we adjust these numbers like the 2 and the minus 4. What happens if my dog is making squeaky toy noises? Sorry about that. Right, so something that we can take a look at now is if we have y equals x squared is our original quadratic function, then if we want to see what happens when we add different numbers to the x before it's squared, that would look something like these expressions. So for instance, if we have y equals and then x plus 4, so parentheses x plus 4 and then close parentheses squared, we see that it moves horizontally, or it shifts left or right. In this case, even though it's an x plus 4, we see that it shifts to the left by 4. For the next one, y equals x minus 3 squared, we shift to the right by 3. And next, for y equals quantity x minus 1 squared, this shifts to the right by 1. So if we were to look at all of these on at the same time, we can see our original y equals x squared, and then we also have these different versions of it that have been slid or shifted left or right. So adding different numbers to x before it's squared is going to affect how it moves left and right. All right, another thing we can do, another thing that you saw happening in our vertex form was that we could add numbers after squaring. So that looks something like this, where we have y equals x minus 1 and then adding a 5 after that. That would look something like this. So this went up by 5, but we can take a look at what the vertex is and see that the vertex is 1, 5. What if we subtract 9 instead? Now this time we see that it shifted down, and in particular the vertex is 1, -9. So the x coordinate is 1 and the y coordinate is -9 for that vertex. And one last thing that we can check in about is what happens if we take that y equals x minus 1 squared, and what if we multiply that by different coefficients? So having different numbers that are multiplying by this squared term. In this case, if we multiply it by 3, the vertex stays in the same place, but the parabola becomes narrower. For this other one, we have y equals -2 times our parentheses x minus 1 parentheses squared. And this one, you might guess, is also going to be narrower, but based on that negative, you've seen in other lessons that having a negative a value means our parabola is going to open downward instead. So just to recap, some things that we saw with this graph are that if we add different numbers to x before it's squared, that's going to shift it left and right. If we add different constant terms, we're adding numbers after we've squared the expression with x, different numbers that are just being added separately, that's going to shift it up or down. And then depending on what the coefficient of this squared section is, that coefficient is going to determine the wideness or narrowness, and then also whether it opens upward or downward. Okay, coming back now to our questions in this next activity, playing with parameters. Without graphing, but keeping in mind what we just saw with those graphs, predict the coordinates of the vertex of each graph. And then also predict whether the graph opens up or opens down. So we'll look at this first one together, y equals x plus 10 squared. I want to just give you a reminder that even though this says x plus 10, remember that when we had x plus something, that shifted to the left. So this one is going to have coordinates. This one is going to have coordinates of the vertex that are -10, 0. And even though this is a -10 in the vertex, looking back at the original equation, our invisible coefficient of this would be an invisible 1. And it's positive, so that means our graph opens upward. For the next one, x minus 4 squared plus 8, we get 4, 8 is our vertex, and it opens upward because there's a positive coefficient here, even though we don't see something that is a positive invisible 1. So that's opening upward as well. The next one has the same vertex. We still have the x minus 4 as the inside part of the parentheses for what's being squared. We still have plus 8 being the constant term that's added, but this time the part that's different is that because we have a negative in front, it's going to open downwards instead. Depending on whatever value we plug in for x, this whole squared component of the equation is going to be negative. So this is going to open downward instead. For the next one, we don't have any shift left or right because it just has x squared. But then x squared minus 7 is going to give us a shift down of 7. Our vertex is 0, -7. And this graph, because the coefficient of x squared is positive 1 in particular, opens upward. The next one, the vertex is -3, because we have our x plus 3 inside what's being squared. Kind of keep in mind, same as factored form, that we have the opposite. So if we were to plug in -3 in for x, that's how we would get a 0 here. So -3 is the coordinate, the x coordinate of the vertex, and then -5 is the y coordinate. Even though this has an a value or coefficient of the squared term that is 1/2, that's still a positive number. Even though it's a fraction, that's still positive, so it's still going to open upwards. And this last one, no matter how big the numbers get, the rules stay the same. So even though it's x plus 100, it still works the same way, that -100 will be the x coordinate of the vertex. This plus 50 will mean that 50 is the coordinate, the y coordinate of the vertex, and the fact that there's a negative leading coefficient or a negative a value is going to mean that it opens downward. So in particular, what this lesson has talked about is vertex form of a quadratic. So unlike standard form, which you've seen that just has each term separately, ax squared plus bx plus c, and different from factored form, where you've seen 2 or more factors multiplied together, and in that factored form we can identify the x-intercepts. What's special about vertex form is that it can easily show us the vertex and whether it's going to open upwards or downwards. So take a moment to read through. As I read this out loud, a quadratic function expressed in vertex form is written as y equals a times parentheses x minus h close parentheses squared plus k. The vertex of its graph is at h comma k. The graph of the quadratic function opens upward when the coefficient a is positive and opens downward when a is negative. All right, that's all for today's Ed puzzle, and remember to complete the 6.15 cooldown by midnight tonight. Remember that you can go back and rewatch any part of this video that you need to, and also remember that you can reach out to your teacher before you take the cooldown so that you can get any questions that you have answered. Good luck!